Hello everyone, my name is Yao Kang from Illinois Institute of Technology. In this talk, I will present our paper, Q-Adaptive, a multi-agent reinforcement learning-based routing on Dragonfly network. This is a joint work with my labmate Xin Wang and my advisor Zhilin Lan. Dragonfly is one of the most popular interconnect topologies for nowadays high-performance computing systems. It is a high-radix topology that can support extreme-scale systems. It also provides high path diversity, such that any point in the system can be reached through multiple different paths. Dragonfly relies on adaptive routing to balance network traffic for optimum performance. Current adaptive routing relies on local information, such as queue occupancy, to estimate global path congestion. As illustrated in the figure, when forwarding a packet, router S prefers path 1 over path 2 because the former has a less occupied output queue. However, in this situation, forwarding packet using path 1 is not the best solution because of the downstream congestion at router A and B. This inaccuracy in estimating global path congestion using local information could limit system peak performance due to the delayed packet delivery or inefficient network usage. In this work, instead of routing based on local information, we propose Q-adaptive routing, a reinforcement learning-based solution that enables routers to learn autonomously about network conditions and forward packet using the minimum time. In the following sections, we discuss Dragonfly topologies and these routing algorithms. We summarize the challenges for designing an efficient routing solution and present the detail of Q-adaptive routing, followed by the evaluation section and a conclusion section. Dragonfly is a hierarchical topology with several identical groups. Groups are all-to-all connected through global links. Routers within the same group are connected through local links. Within this work, we focus on the topology as shown in the figure with all-to-all intra-group connection, because this is the structure that will be deployed on the next generation HPC systems. Dragonfly is a diameter 3 topology such that packet can be delivered within 3 hops, including 2 local links in source and destination group and a global link crossing groups. For the purpose of balancing the network usage on local and global link, Dragonfly is usually configured with P equals to half of A, where P is the number of compute nodes per router and A is the number of routers per group. Dragonfly routing is usually evaluated under 2 extreme traffic patterns. In the uniform random pattern, each node selects randomly its destination. UR pattern is considered as the best case on Dragonfly system because in the system, network traffic is evenly distributed. Under the adversarial traffic pattern or ADV plus I pattern, messages generated in group G are all targeted to group G plus I. The figure in the middle shows the traffic movement under the pattern of ADV plus 1, and we can see that under the minimum routing, global link between neighbor groups can become the bottleneck and can also be heavily congested. The global link congestion can be avoided by routing packets through an intermediate group. However, as illustrated in the figure, under the ADV plus 4 traffic pattern, local link in intermediate group can also become the bottleneck and be highly congested. As a result, this global and local link congestion make adversarial traffic pattern be considered as the worst case scenario on Dragonfly systems. Dragonfly routing can be broadly classified into non-adaptive routing and adaptive routing. Minimum routing is a non-adaptive routing method that it forwards packets using the shortest path. Minimum routing is the optimal solution for the UR traffic pattern. However, it performs the worst under the adversarial traffic pattern. Valiant non-minimum routing is the optimal solution for the adversarial traffic pattern by forwarding packets through intermediate group to bypass global link congestion. Depending on how the packets are forwarded in intermediate group, valiant non-minimum routing has 2 variants of VALG and VALN. As shown in the figure, VLN can bypass local link congestion by rerouting packets through a randomly selected router in the intermediate group at the cost of one additional hop. Adaptive routing forward packet either minimally or non-minimally according to the network condition. UGAL is a widely used adaptive routing solution that it lets the source router make a one-time adaptive routing decision. Depending on the used non-minimum routing path, UGAL has two variants of UGALG and UGALN. Progressive adaptive routing, or PAR, improves UGAL but lets the routing decision be re-evaluated in the source group, such that a previously made minimum routing decision could be revised to follow a non-minimum forwarding path if the packet encounters local congestion in the source group. In this work, we model the Dragonfly routing problem as a multi-agent reinforcement learning process, such that each router is considered as independent agents. And by interacting with the environment or the network system, routers learn to forward packets using the minimum time. Queue routing is a pioneering work in applying RL technique for network routing. In queue routing, each router maintains a queue table that contains queue values. Queue values are the estimated packet delivery time from the current router to different destinations. For example, when router X receives a packet for destination R1, it firstly reads the table to find the port with the smallest estimated delivery time and forwards the packet through that port. Assume the packet is forwarded to router Y, and then router Y and all the other downstream routers forward the packet in the same way. After router Y forwards the packet, it also returns its own estimated delivery time and a reward back to router X, where the reward is defined as the packet traveling time between router X and Y. Once router X receives the feedback, it updates its queue value according to the formula shown in the figure. Queue routing is a good starting point to investigate RL routing on Dragonfly systems because it is simple and lightweight. However, queue routing has several limitations. First, it's only tested on small-scale systems. In contrast, nowadays Dragonfly system usually consists of hundreds or even thousands of routers. Queue routing cannot handle global or local link congestion efficiently, and it may also lead to routing levellock and deadlock on Dragonfly systems. In queue routing, the queue table size is linear to the system size. As a result, rarely visited destination could lead to outdated queue value problem, and this outdated value could lead to system instability and slow convergence. The first challenge for designing an efficient routing algorithm for Dragonfly topology is coming from the topology uniqueness. Dragonfly is a high-path diversity system, such that how to select the best forwarding path among all the available candidates is difficult. An efficient routing algorithm should be able to handle both extreme traffic patterns at the same time, and it should also be able to avoid local and global link congestion. An efficient routing algorithm is expected to be able to handle the routing levellock and deadlock problem using limited resources. And in a distributed learning environment, routers are considered as independent agents that can only partially observe the system state. Therefore, routers should be coordinated between them. In addition, we wish to avoid heavy implementation requirements such as additional wire connection or heavy computation requirements. In response to the previous challenges, we present queue-adaptive routing. Queue-adaptive routing comes with a novel two-level queue table. When forwarding a packet, a router first identifies to which group the packet is going to, and from which node relative to the source router the packet is coming from. With these two information, the router can read the queue table to find the port with the smallest estimated delivery time. The novel two-level queue table is 50% smaller than the original queue table by cutting half of the rows. A smaller queue table consumes less memory, and it also avoids outdated queue value problem due to sparse updates. By embedding both packet source and destination in the table, routers can learn from these two informations to leverage the high path diversity feature provided by Dragonfly topology. The flowchart on the right shows how a router makes a routing decision when it receives a packet. In most of the cases, packets are minimally forwarded except at two locations, the source router and the first router in an intermediate group. At these two locations, a router can solve the two-level queue table and use the learned information to select the best forwarding path among all the available candidates. Queue-adaptive routing can guarantee a packet be delivered within 5 hops, and as a result, compared with adaptive routing algorithms, queue-adaptive performs similarly by forwarding packets either minimally or non-minimally. However, instead of always using local information or always rerouting packets in the intermediate group, queue-adaptive can avoid global and local link congestion dynamically through the learned information under the help of two-level queue table. To update the queue table, we leverage two previous work of distributed queue learning and hysteretic queue learning. In distributed queue learning, routing policy is only updated in the better direction, and it ignores penalties. It proves system convergence, however, it may require a long time to converge. In hysteretic queue learning, it leverages two learning rates to update the routing policy in good and bad directions separately. The benefit is that it does not have any specific initialization requirement. Inspired by these two works, we proposed to update the queue values using the formula shown in the figure. In response to the challenges, queue-adaptive routing can avoid global and local link congestion by selecting the best forwarding path among all available candidates. It delivers packets within 5 hops, thus routing deadlock is no longer a problem, and it avoids routing deadlock using limited resource. Queue-adaptive routing is a fully distributed method that it does not use any shared information. Each router is considered as an independent agent, and they are coordinated through the two learning rates. For the implementation cost, queue-adaptive routing is a computational light solution. It does not require any specific hardware implementation. It does not require any additional wire connection. It also uses a smaller queue table to save router memory. In this work, we implement the proposed queue-adaptive routing in SST Merlin simulation toolkit and publish our code on GitHub. SST Merlin provides high-fidelity, fleet-level interconnect topology simulations, and in this work, we evaluated with two systems, a 1K system with more than 200 routers and a 2K system with more than 500 routers. Both systems are considerably larger than the original queue routing study, and the detail of the system configuration can be found in the paper. The figure on the right shows the evaluation result of average packet latency, system throughput, and hop count under different loads. Under the UR traffic pattern, queue-adaptive can achieve up to 5 times average packet latency reduction compared with PAR. And under the extreme system load, queue-adaptive can achieve up to 10% system throughput improvement. Under the ADV+1 traffic pattern, queue-adaptive always has the smallest average packet latency compared with all the other evaluated routing algorithms. And under the ADV+4 traffic pattern, queue-adaptive performs similarly to PAR regarding both latency and throughput performance. This figure depicts the packet latency distribution with the zoomed-in plot shown on the top. We observe that under both UR and ADV+1 traffic pattern, queue-adaptive achieves the smallest 99th percentile latency. Although under the ADV+4 traffic pattern, the 99th percentile latency of queue-adaptive is slightly larger than that of PAR. However, we observe that queue-adaptive has a more compact latency distribution, such that more than 80% packets could be delivered under 2 microseconds, compared with only 63% with PAR. The two plots on the left show how the network responds from a cold start on the various system load and different patterns. We observe that queue-adaptive can converge under 500 microseconds. The two plots on the right shows how Q-adaptive performs under a dynamic system, and we observe that Q-adaptive can nearly instantly respond to a network load change. We studied the scalability of the proposed Q-adaptive routing on a 2K system, and we evaluated both extreme traffic patterns and 3 representative HPC communication patterns, which are 3D stencil, many-to-many, and random neighbors. The figure depicts the packet latency distribution on the 2K system, and we observe that Q-adaptive routing achieves the smallest average packet latency, with the smallest 99th percentile latency compared with all the evaluated adaptive routing algorithms. In conclusion, Q-adaptive is a fully distributed, highly scalable, multi-agent reinforcement learning-based routing for Dragonfly systems. It does not require any additional hardware implementation or additional wire connection. It does not use any shared information to save network bandwidth, and it comes with a novel 2-level Q table that contains more information in a smaller size. The evaluation results show that Q-adaptive routing can achieve up to 10% system throughput improvement and up to 5 times average packet latency reduction compared with existing adaptive routing algorithms. At the end, we would like to thank our Shepherd and the HPDC reviewers for their valuable feedback and insightful comments. Thank you for your attention.